Okay, so hi everyone. Thanks for joining. Today it's my pleasure to introduce Luc de Raedt. I hope I got that right, who's a professor from KU Leuven. And he's the director of Leuven AI, the newly founded KU Leuven Institute for AI. And he's been doing a lot of great work on AI, machine learning, data mining, and their applications, and especially in the area of learning and reasoning. And I think that's some of the work that he'll be talking about today. He's a EurAI and AAAI fellow, as well as an IJCAI trustee, and recently received an ERC Advanced Grant in 2015. So yeah, thank you so much for joining us today. And with that, I'll hand it over to you.
Okay, thanks for having me. So the story that I want to bring today is like going from statistical relational AI to neuro-symbolic computation. And of course, it's joint work with many people. And the most important ones are mentioned here, like Robin, Angelica, Giuseppe, Sebastian, Thomas, and Thomas. Okay, so I guess this kind of book is pretty famous. Everybody talks about it in AI. It's about system 1 versus system 2, thinking fast and slow. It appears in different ways as data-driven versus knowledge-driven, symbolic, sub-symbolic, solvers and learners is what Hector Geffner uses. And I guess everybody agrees that this is like the way to go. The thing that people don't agree about is like how to get there, and there is where the differences in opinion are between maybe people coming more from good old-fashioned AI and people more coming from the neural network side. And of course, this is also what you need in practice. This is a kind of typical question you have to answer if you go to get your driver's license. You get an image and you have to analyze it. You have to recognize where the different entities are, the cars and the traffic signs. And then, of course, that's like a perceptive component. But on the other hand, you also need some kind of knowledge to reason about who can go first, in a sense, on a kind of crossing like that. And so you really need perception and reasoning. The question then is like, what's the state of affairs in AI? And I guess if you look at the main paradigm in AI today, I mean, it's neural networks. It's all about thinking fast, and it's all about learning. And but there's also been a lot of progress in reasoning techniques where the two main paradigms for many, many decades already are probability and logic. And what you have as well in about these two paradigms, that their integration has been very well studied in statistical relational AI or probabilistic logic programming. And they've also like added learning components on top of that. If you look at the book, The Master Algorithm from Domingos, then he talks about unifying like 5 different schools of machine learning. And today I'm going to talk about trying to unify 3 different schools of them, namely logic, probability, and neural networks. If you look at certain combinations, then logic and neural networks is often viewed as neuro-symbolic computation. I mean, this is the area that combines logical reasoning with neural networks. And so my first key message and my arguments will be that these fields of starry probabilistic logics and neural logics, that they actually have a lot in common, that many similar problems do apply, and that therefore some of these solutions that have been developed in starry are also applicable to neuro-symbolic computation. We actually wrote a survey paper about that at IJCAI a couple of years ago. There's a long version on archive where we go over 7 different dimensions, really making that point hard. Of course, this is not the only view on neuro-symbolic. I mean, people sometimes use neuro-symbolic to talk about the language, the words being the words in language being the symbols. So it doesn't cover everything, but it's still like from a reasoning perspective, it's probably a key aspect. If you look at the state of the art of neurosymbolic computation, then what most approaches are doing is they take the logic or they take the knowledge and they kind of transform it or inject it into the neural network. And then the neural network is supposed to do all the reasoning. And the downside of that is, of course, that you lose the power that typically is associated with purely symbolic representations, namely reasoning, kind of also being able to do explanations and to get some trust. I mean, all of that seems to be lost if everything is left to the neural network. And that's why my second message is that I think it's time to try a different approach. And in that different approach, if you talk about a true unification or a true integration of different components like X and Y, then you basically want the originals to have them as a special case. So what Neuro-Symbolic should be doing, if Neuro-Symbolic is supposed to integrate logic and neural network, then it should have both logic and neural networks as special case and all the abilities of the two, so to say. And in that regard, 1 + 1 becomes 3 in a sense. That's my second argument. I will illustrate that with some of our work on the Problog, which is kind of a neural extension of a probabilistic programming language. I'm also going to talk a little bit about Deep Stocklock, a little sibling of that language. But let me first go to this going from star AI to Neuro-Symbolic, or from logic and probability to logic and neural networks. And as I said, there is this key message that there was a lot of similarities in terms of the problems and the representations being used, and that therefore very similar solutions apply. One thing that occurs both in logic, in graphical models, and in neurosymbolic models is basically that there's kind of two variants. And you can look at that starting from the logic, and then I'm going to go to the other components. Here you've got a very simple, simplistic kind of probabilistic logic program. There are some facts that are true, like burglary is true, Mary hears the alarm, the true facts are stated. And then you also have a couple of rules, like a rule that says Mary calls if the alarm goes off and Mary hears the alarm. So the typical kind of if-then rules just formulated in Prolog, the kind of implications that typically come with that. Once you have a logic program like that, you can build proofs. And here is a proof tree. There was actually two derivations that prove that Mary calls, and the typical mechanism is like, you know, resolution as it's always gone. I don't think I need to explain a lot about that. It's backward chaining that is going on here, and there is two proofs. And that's like one perspective. This is really like the proof theoretic perspective on logic. There is the other perspective where you view logic as constraints, and you do it more in a model theoretic fashion. And that's the perspective that is taken in SAT solvers, that is where you're given like logical statements, like the ones listed there. Mary calls if and only if she hears the alarm and the alarm goes off. And then you're looking for possible walls, so-called models, that satisfy the requirements, the conditions imposed by these constraints, by these logical constraints. And that's like the model theoretic perspective that you have. Now, it turned out that this perspective from logic, that it really carries over to probabilistic graphical models and also to this star AI systems, because in the star AI systems and these graphical models, you have like the directed versus the undirected view. And here you see the standard Bayesian network that is directly mappable onto a logic program. And that's kind of the directed version. On the right hand, you see more the Markov network, the Markov random field, the Markov logic perspective, where you have like statements and the weighted statements. And the idea is that the higher the weight, the more important, the stronger the constraint is actually becoming. And that perspective is what you get in graphical models, but also that perspective is very fundamental in neurosymbolic systems, because there again seem to be two kind of representative schools or approaches. In the one hand, on the left, you have like neurosymbolic approaches where the program, so to say, is used to determine the structure of the neural network. And on the other hand, on the right hand, you have like the constraints, the logic is used to kind of regularize the neural network. And this is more acting as soft constraints. And that's like, so this parallel carries over from logic to graphical models to neural networks. And it's kind of instructive to go back to the early days of Neuro-Symbolic. One of the very first approaches, if not the first, was that of K-band by Towel and Shavlik already in the 90s. And what they did is they would start from this very same propositional programs that I was showing with Mary and hearing the alarms and so on. What they would then do is they would kind of rewrite that programs into a kind of proof tree structure. I mean, here you see kind of and/or structure that actually is there to prove A from the kind of leaves of the tree, which would be given in a sense, and then you would try to prove this. That's like a purely logical step. The next step, what they then did is they would take that proof tree structure or this and/or tree structure, and they would turn that into a neural network. Basically, the nodes in this proof tree, they would become nodes in a neural network, and they would add further connections. And of course, they would add weights to these connections. Perhaps they would add here and there some hidden nodes that didn't appear anywhere. And then they would just train this neural network as usual. And this was like one way of incorporating logic and structure into a neural network. They also studied the reverse problem. Once you have the neural network, can you still reconstruct the rules from that neural network, which is in a sense looking for explanations into that kind of structure. Now that approach from K-band is still very popular today. Of course, people use much richer representations. Here you see approaches due to the Kuzelka group in Prague, where basically you have like logical rules, prologue rules, and they kind of made fuzzy. And then you build this kind of proof trees. And again, you do the kind of things that are popular in Starry and that actually carry over to Neuro-Symbolic. Also, the neural tier improver is, in a sense, coming from that perspective. The neural tier improver, there you start from a knowledge base like the one that is listed in the top left of the slide. There is a couple of facts like Abe is the father of Homer and so on. And then you also have like these rules, grandfather of X is the grandfather of X of Y, if he's the father of Z and so on, basically the typical kind of rules that you get in this kind of situations. And then what NTP does is it actually builds also a kind of proof structure, and that proof structure is turned into a neural network that is trained afterwards. Now, one of the very fancy things, very appealing of the neural tier improver is that whereas if you do pure tier improving or these derivations with these rules, you would want to get exact matches, like grandfather of should match exactly with grandfather of. That's unification, logical unification. That's hard. And what they managed to do is actually to make that soft unification so that it would also match if it's close in embedding space. Like grandfather of would match with grandpa of because they're pretty close in embedding space. And that's a pretty attractive feature of that approach. But in essence, what they're doing is something very similar in spirit to K-band, but with much richer representation and much richer possibilities. In both cases, what you have is that the logic is encoded in the neural network, And once it's in a neural network, it's no longer possible to really reason at the logical level with that. All what you can do is like answer certain queries at the end, but the kind of reasoning that you could do with the pure logic is to a large extent lost. There's also the other perspective, and that's to use logic as constraints. And here there's a very interesting example from the group around Guy van den Broek in UCLA, where he's using logic as constraints. And again, it's a propositional setting. Suppose that you're doing multi-class classification, and there's like 3 classes, 1, 2, and 3. And so you have these output nodes. And then if you train it, well, the output values could be 0.8, 0.3, and 0.9. But of course, that's something that you probably don't want, because if you do multi-class classification, there should be exactly one of these that is true and the others should be false. And so you could imagine enforcing a constraint that says exactly one of the 3 output categories should be true. You can write it down in logic as is done here. And then you can look at the probability that for this class 1 of 80%, class 2 of 30%, 3 of 90%, that this constraint is satisfied. And so you get the expression that's on the right. And so what they compute is the probability that the constraint is satisfied, and they use that as a kind of semantic loss. They actually the higher the probability that it's satisfied, the lower the loss is. And they then combine this semantic loss with a kind of traditional loss, and have some nice theory around it, and also some nice experiments that show that this really, really works. And again, that principle, that idea of using logic as constraints is very popular today. I mean, if you look at systems like the logic tensor networks by Serafini and Garcet, or semantic-based regularization from the Siena group, then again, you will see that there is like logical constraints that are kind of turned into the neural network and that are used to really regularize the loss function and to penalize it. But again, in these approaches, you lose the ability to reason logical once the neural network has been trained. And that's something that I don't think is a good thing, because, as I said, what you really want, if you combine logic and neural network, you want the ability of both, in a sense. And in this way, one ability is delegated completely to the neural networks. Another kind of dimension that you can look at when you map star AI and to Neuro-Symbolic is the numbers. What do they really mean? And again, there is a lot of analogies to be made there, because you can go from logic to probability, and also to fuzzy logic. And that's also what people in star AI do. There are 3 types of approaches to Neuro-Symbolic. There are approaches that try to keep everything logical. The group around Ziwa Zhu in Nanjing is actually trying to do that in some of the approaches. The downside is that it's, of course, very hard to optimize, because you have to cope with this 1-0 kind of problems. Then there is the probabilistic approaches, like the one mentioned with semantic loss. And most of the approaches are actually using a fuzzy logic. And they're not doing that because of the properties of fuzzy, but because they prefer fuzzy logic over probabilistic logic, but largely because it's a lot more, it's computationally much more effective to use the fuzzy logic. And that's, again, very similar to what you have in statistical relational AI, because also there you have like these different stages that you can use. And don't think I'm going to go into the full details at that level, because that's a bit more technical, and it's easy to get distracted here. But essentially, with these probabilistic models, what you get is you associate probabilities to some of these facts, and then like burglary and alarm, and then that induces a probability distribution over these possible walls. That's what you have. The probabilities are really on the facts, and then you get, by extension, that the semantics is over possible walls. If you look at something like Markov logic, you associate weights to constraints or to logic, and then the idea is that the higher the weight is, the more important it is. And in the case that the weight becomes infinity, then of course you have a hard logical constraint. And then you can also use these constraints to determine probabilities of the possible walls. And I guess it's pretty well known how to do that. A step further is to do what also PSL does, probabilistic soft logic, because there you have, again, that the weights are associated to the constraints, but on the other hand, they would also like interpret these possible walls together with probabilities. So the facts would get a belief function that is associated, or a kind of degree of certainty, a membership function in the fuzzy logic. And then they use that to look at the degree to which these logical constraints are satisfied, together with T-norms and particular fuzzy operators. And you get a whole system that is kind of easy to manage computationally, but a lot of the intuitions that do hold for logic and for probabilistic logic do not longer hold for these fuzzy logic. And that is sometimes forgotten, because if you look at a fuzzy logic, it doesn't necessarily hold that if A implies B and B implies C, that you also have that A implies C. And that's something that you do have in the other kinds of logic, and that is kind of intuitive as well. So certain things that intuitively hold may no longer hold in these fuzzy approaches. And it is, again, this fuzzy approaches that is pretty popular in the literature. Again, if you look at things like logic tensor networks, the semantic-based regularization, lifted relational neural networks, they all use a fuzzy logic to make the computations scale up and scale up faster. And okay, you do pay a price to do that. And yeah, because you pay a price to do that, our approach is different. We really try to get the probability, the probabilistic framework, the logical framework, and the neural network as special cases. And we're gonna try to illustrate that with our dproblog, which in a sense provides an interface layer between the logic, the probability, and the neural network. I want to stress that an interface is not a pipeline, because there is a flow of information in all kinds of directions. It's not in a pipeline, it's only in one direction usually. So what is dproblog? Well, dproblog is based on this probabilistic logic programming language called Problog, and is then extended with neural networks. If you compare dproblog to a lot of the related work in Neuro-Symbolic, then you get the full expressivity of a programming language. Problog and dproblog are programming languages, so you get the full expressivity there. You get the logic and the neural networks as special cases, and you do retain a very clear semantics. I mean, in probabilistic programming and in programming languages, it's important to have clear semantics. Well, for dproblog, it's based on that of Problog, and you get that in a sense for free, these semantics. I'm going to go in two steps in introducing this. First, I'm going to go from logic to probabilistic logic, and then I'm going to go from Problog to dproblog in a sense. So let me start with the beginning and showing again this very simple, purely logical example where you have these propositional programs and you have proofs. Now, Problog is based on what is called the distribution semantics, which is due to Sato and Poole. And the kind of seminal insight that Sato and Poole had was that in order to get a probabilistic logic, what you need to do is to unify the basic concepts in logic and probability in the simplest possible way. And so what they used is like propositional variables become random variables. And by doing that, you get this interface between logic and probability. And they translated that idea into just this probabilistic language where the only thing that they needed to do was basically associate probabilities to facts, as you see on the right. The facts become probabilistic, and they're kind of independent, they're marginally independent of one another. And that's very similar to what you have in a Bayesian network. If you look at the Bayesian network, then also the nodes without any parents, they're marginally independent of all the rest if there's no evidence. And that's the same situation that you have here. The dependencies are introduced via the rules, and the rules is all you need to make this work. You can then look at how to extend that to the proof theoretic perspective. And if you have this kind of probabilistic programs, you can of course get probabilistic proofs. Here there is two proofs. There is one proof for alarm via burglary and one for earthquake. And the probability of one proof is just the product of all the facts that you use along that proof, basically. And so it's tempting to say that, well, the probability of alarm, it's the probability that one proof succeeds or that the other succeeds. It is tempting to replace the or by a plus, but that is, of course, illegal because if you take the probability of a disjunction, then you should also make sure that you subtract the intersection, the conjunction, so to say. So the probability of alarm here is the probability of burglary plus that of earthquake minus their intersection, which is burglary and earthquake. And that is leading to computational problems. I mean, that's leading to the Sharpie completeness of the inference in a sense. You can also view these programs as kind of generative models, and that's the perspective shown on that slide. Here you've got a program, and it's also using this little variation, what we call annotated disjunctions, where there's rules the third rule is actually saying if there is an earthquake, then the alarm will go off with a particular probability. And there could also be something else that happens with another probability in that case. Now, these rules can be understood as generative processes. And so in the tree, you start with the empty model. Nothing is true. You then go through your rules and you look at the first one that fires, that's earthquake. So just below that empty node, you get the node that contains earthquake. Third rule then fires. If there is an earthquake, either the alarm can go off and you go left, or it doesn't go off. And so in the nodes here, you've got earthquake and alarm. Here you've got just earthquake, and you can kind of recursively unfold. You can recursively build up that model in all possible ways in this kind of tree. And at the leaves of the tree, you get the models of your program. And what you also see is that you can look at the probability of getting exactly in one of these leaves. It's just taking the product of all the probabilities and counter it along the path. What is then the probability that the alarm goes off? Well, it's the probability that it's the sum of the probabilities of all the leaves in which alarm is occurring. And in this case, it's the orange ones that you have to add up, and these are the resulting probabilities. Why are we having these probabilistic programs? Well, it's very easy to represent, graphical models like these Bayesian networks, in that it maps directly on this kind of programs. It, of course, also easily extends to richer notations like these plate notations, where you have like two plates here, one for student, one for course, and it's the intelligence of the student that determines the grade, and the difficulty of the course that is determining the grade as well. And then you have the typical kind of unrolling. If you now fill out certain students, fill out certain courses, you get this kind of network situation. It's very easy to map all of that onto Problog, because essentially what you need to do is every entry in a conditional probability table is turned into one of these rules. The red rule is here covering the case that the student is intelligent, the course is difficult, and then you get probabilities that he gets an A, a B, a C, and so on. It's easy to change the number of students and the number of courses, and so you get the typical SRL star AI, the database, the logic perspective. What you also get for free with these representations is that you can just encode logical rules, ontologies, like when students perform satisfactory or unsatisfactory, you just write them down in rules, and you can do all the kind of reasoning and, of course, all the kind of learning that you typically do. So how does inference work in these cases? Inference is actually going through 4 steps. In the first step, you look at your program, and then you have, in this case, there is also like some variables appearing like X, some entities or constants that appear like Mary and John. And the first step is really to ground out your program. And you do that by systematically replacing the variable by the different constants that you can get. Then you're going to rewrite the logic program into a propositional logical formula. And in this case, it's easy, but for recursive programs, it's quite a bit more involved to do that. And so you get this logical program, which this logical statement, which you can then compile into a circuit with standard knowledge compilation techniques that are known from the knowledge compilation technology, and once you have that, you can actually replace the and the or by plus and multiplication, and you can do the kind of computation. And so this arithmetic circuit is actually dealing with this disjoint sum problem. Once you have the circuit, inference is very, very efficient. It's just going up and in one pass and computing the probabilities. We've done quite some applications with this. These are like applications in modeling massive multiplayer real-time strategy games, admitted in limited environments. I mean, like with a couple of 100 players. We've also done it, used it to track, for instance, and to reason about occlusion. On the right, you see that you can keep track of positions of occluded objects if you have the right kind of series. There's been techniques to do learning in robotics settings with a kind of extension of Problog towards continuous distributions, where in the first step, also on a real robot, a real iCub, we were able to learn displacement of objects if you do certain operations on that. Once you've got the kind of learned rules, you get a kind of planning operators. It's a bit like probabilistic strips, but with continuous distributions. And then you can start to reason with that and to plan with that in order to reach certain configurations on a board. There's applications in biology. If you want to try it out, just go to our website where you can try it out. There's an online interface where you can actually use it. But that's Problog, and I promised to talk about deep Problog, the extension toward neural network. And if you look at neural networks, in again, the simplest case, taking the analogy with Sato and Poole, what's the simplest way to kind of incorporate neural networks into a framework like the Problog? Well, a simple way of doing that is to take a neural network and to consider it as a neural predicate. As an example, take these MNIST images that you can map onto, of course, one of the 10 classes, the one digits that you have. And if you can interpret the output as a probability, then it kind of makes sense to turn that neural predicate into one of these probabilistic facts, this kind of annotated disjunctions, so to say. And that's the only thing that we added to the Problog, to get deep Problog. That's a notion of a neural predicate that becomes a neural network, and that provides an interface between the logic and the neural network, and that's actually all you need to do some stuff. And so what you do here is like you declare this neural predicate that is this digit. The first argument of that neural predicate is an image, an MNIST image, and it maps onto a particular output, well, one of the digits between 0 and 9. And then if you have a digit like an MNIST image like this, this one here, then it's going to be mapped onto one of these annotated disjunctions. It basically says the probability of that fact is 0.4, 0.35, and so on. And of course, the sum of these probabilities should be equal to 1. And that's actually
Luke,
all
I have
there
a quick
is.
question.
Yes?
So sorry to interrupt your flow, but you're assuming here that the neural predicates are pre-trained somewhere else before they go into Problog, is that right?
No, we don't. That would be too easy.
That would be too easy. So sorry, are you about to get to that part, or
yes,
is it obvious?
I'm coming there directly. And that's the interesting part, because it really provides you an interface with the logic. And here is the example. So what we provide as knowledge here is like, you take 2 of these images, like 3 and 5, and you want to compute what the result is, like 8. So the examples you give are addition 358, addition 044, and so on, basically. What you also give is background knowledge. And you do know in this background knowledge how to perform addition. The only thing you don't know is how to map an MNIST image onto a number. And that's indicated here. Like, so the addition predicate is basically very simple. If I fill out now like this first example of this MNIST addition, then I fill out 358. And what the rule tells me is you first have to map the image 3 onto a number and 1. Then you have to map the second image onto a number and 2. And the sum of the 2 numbers must be equal to 8. And that background knowledge acts as a constraint on the learning of the neural predicates. The examples you give are just at the level of addition. The examples you give are not at the level of digit. It's kind of automatically with a kind of abduction. This is going to be trained. And you see why this works. It provides you with constraints. We've then tried that out with a, we've compared it to like standard neural networks, of course. And yeah, as expected, given that deep Problog has more knowledge, it converges faster to the right kind of classifications of the MNIST images. Now, this is not very impressive. I mean, it's just about 1 number, but this is already a lot more interesting, where you take like, you know, sequences of these MNISTs, and you give examples at the same level, like what is the sum of these two sequences of MNIST images, that are the examples you give. And all what you need to do in order to capture that is, again, digit is this neural predicate. You don't know which numbers the MNIST should map to, but what you do provide is background knowledge about the way to do addition, and that's just changing, you know, the Prolog program a little, and then you can see that it also works for this case, that you automatically will find you know, the right mapping with examples that are a lot longer than just the single digits, so to say. The cool thing about Deep Problem was that conceptually it was very, very easy to develop. And also from an inference perspective, because what you get is like all the machinery that we had for Problem carries over to Deep Problem. And in a sense, what you get if you apply the standard machinery of Problem is you get the circuit back. And at the leaves of the circuit, what you're going to get is not the probabilistic facts, but you're going to get these neural predicates. And so in effect, these neural predicates, well, underneath, there's kind of this neural network that occurs. And what you then can do is, like, as usual in neural networks, you start with your loss function at the top, and you just do gradient descent. You push down the loss into the weights, and you train as usual with neural networks, and the parameters of both the neural network and the probabilistic program are trained together. The other thing that was cool to do is we had like kind of semi-ring extension of Problem, which is called a Problem. A Problem works for any kind of semi-ring, and there is this kind of gradient semi-ring that you could just apply. And so in a sense, from an implementation perspective, we could also use that machinery, and it was pretty light to develop. Of course, we've been doing experiments. We've been doing experiments to compare to some other works in rule induction approaches with neural networks. What people tend to do is they use this kind of templates, and then they fill out the predicate variables. I mean, this P, R, and Q, they will replace by, you know, normal predicates. And we didn't do it in this way, but we take the approach that was also in differentiable force, where you've got like programs with holes, this kind of templates that you have, and then you can try to fill them out in a sense. Here is one of these examples. There is a bubble sort program, and you don't know like when to swap two numbers, and that is then turned into that neural predicate. There is this hole, so to say, that you try to fill this kind of sketch. I should use, certainly if Armando is present, I should use that terminology, and I usually use that. Just that I couldn't find the word right now, but and yeah, then you see that the Problem does better than differentiable force. We've tried some other things like with some simple word algebra problems. Yeah, some things like addition again. Another thing that's interesting is that this noisy addition, it's again a very toy problem. But it shows what it can do in a sense. This is a variant of the addition, the single digit addition. And the variant is that with a particular probability that's indicated by this noisy variable, you will take a uniform output, a random output, so to say, and with probability 1 minus that noisy, you take the true addition. And then what you see is that in this example, both digits and noisy are trained, the parameter of noisy and the parameters of your neural network. And so you learn also the fraction of noise that you have in your data. And that's what you see, like with different increasing fractions of noise, you see that it performs pretty well and actually recovers the amount of noise that you have in your data. We've done things with simplified pokers because that's a real probabilistic setting. One of the difficulties with the original dproblog is that it doesn't scale up that well, but that's been solved by now. It's a lot better. Now there is techniques that will not look for all the kind of proofs, but will look for the best proofs. And that scales up a lot better. These are earlier experiments. As I said at the beginning, we are fascinated by this neural tier improver because there you have like grandfather of and grandpa of that are close in embedding space. And you can do this kind of soft unification with that. You can really match this two kind of predicates. And that's something you can easily simulate in dproblog. And the example that we have is indicated here. You can look at like two MNIST images. You can kind of embed them in a neural network, and you can then define the distance between the two to be, for instance, based on this radial basis function. And you can define this as a kind of soft unification. What we do here is in this predicate, you don't say like it should be similar, but you basically take two digits, two MNISTs, and you look at how far they are from one another. So 3, 5 is 2 at the distance 2. And what you do is you embed the 2 digits. You also learn the kind of successor vector, and then you do operations in the logic where you multiply, in this case, well, the difference is 2, so you multiply that vector by 2, and you get that the resulting vector should be close in embedding space to the original vector, and that's very similar in a sense to the idea of trans E. If you train your program like that, what you will see is that you get this kind of situation as on the right, where they really like the numbers are mapped onto something that's one apart from the other on this kind of line. We've done other things with the clutter data set and so on. Let me conclude by looking at this little sibling of dproblog, which is called deepstocklock. And that's actually based on stochastic logic programs. I mean, in Staria, in probabilistic logic programs, you have like 2 versions. One is the probabilistic logic programs, and that's very similar to graphical models. The other is the stochastic logic programs, and that's very similar to probabilistic grammars. And in this deepstocklock, we apply the same methodology, the same idea of getting neural predicates to this SLPs in a sense, and that's more recent work. And the advantage is that it scales a lot better than dproblog. Here is an example where you get that. On the left, you see this kind of stochastic logic program written as a definite clause grammar, where you have like these 2 non-terminals with corresponding probabilities, and where you also can do some computation of the kind of results. And so what you can parse here is like the kind of expressions that you see at the bottom, like this 2 + 3 + 8. You can actually parse that and kind of compute the results with something that's very close to the neural predicates. And this is more efficient than the other version. And it's of course also working with sequential situations. As I said, there is challenges. I guess one of the challenges is to make it scale up. And there, yeah, you have to resort to approximate inference. Exact inference is too limited. But yeah, we've got a version working on with an A*-like algorithm to find good proofs. And yeah, we're also looking at kind of expanding the applications and yeah, also looking at a little bit of robotics, but it's very early days to do that. Let me conclude by repeating the key messages. The first is that a lot of the ideas and techniques and problems that arise in Starry actually reoccur in very much the same spirit in Neuro-Symbolic. I talked about like 2 dimensions, but in our paper you find 7 different dimensions that actually are shared between these 2 fields, and that's yeah, I think that gives insight into what's going on. And the second thing is that, well, we believe that with these neurosymbolic systems, you should get the logic as well as the neural network as special cases. And that's also what you see in this deep problem approaches. So thanks for listening.
Okay, yeah, thanks so much for the great talk. And yeah, I guess we can open the floor to questions. Yeah, feel free to just unmute yourself and ask a question. So maybe to get started, I had a question about, so I guess one important aspect of human learning is that, you know, we're not just, I think a lot of times, like in your example at the beginning of the car, it's not just the kind of neural network or detection that needs to be learned, but actually also a lot of these rules that you kind of talked about as background knowledge. Also, you know, humans are also capable of learning that. So I'm wondering if you have any thoughts on whether that's something that's possible in this framework.
So first, I think the key advantage of this kind of approaches is that you can use knowledge whenever you have it. I think that's the reason for using this, because the knowledge can be a shortcut to training. Like in the example with the traffic exam, the driver's license. I mean, yeah, there's no way of learning the rules of the traffic. I mean, you really want yeah, this to be given. It is given, so you'd better use it if you want to learn. Having said that, there are these approaches that work with I mean, like the approaches of Rich Evans, for instance, that work with these templates of rules and then kind of use these predicate variables, and then would like replace these predicate variables by particular predicates and kind of evaluate that. This kind of approaches do exist. That's something we haven't elaborated too much on yet. We plan to do so. We also know how to do that. But that structural learning, I think, can only be partial. I don't think it's, yeah. I don't think you can learn everything, so to say, both the neural network and the structure at the same time. You have to start with something. And yeah, that's what I feel in a sense.
Yeah, that makes sense. Thanks. Yeah, are there other questions?
I was wondering if oh, sorry, go ahead.
Yeah, I'll be quick. I had a question about the neural attributes. From what I can remember, the output of neural networks to interpret them as probabilities is often unreliable in that they can be very overconfident. And I was wondering if you could speak about any experience you have with instances where the attributes should have probabilistic values and whether the inference was able to proceed. Like, did you run into any issues with, because I think a lot of the examples you gave, the output of the neural network had a correct answer. And so the probabilities, if they converge towards 1 for a specific class or prediction, that was like the correct input to the rest of the program. Yeah.
Yeah, so like one of the difficult things, one of my students actually spent a lot of time on that, trying to understand. I mean, in the first example, we use like 2 single digits, images, I want to predict a number, but we're looking at like, what if, can't we like learn with 3 images, so to say, a 1 + 2 gives you 3, and it's all like unmissed images. And in that case, what it did learn was something pretty cool in a sense, but also frustrating, because it actually learned consistently 0 + 0 is 0. So it was learning, something quite unexpected. And it of course makes perfectly sense, because that's the simplest model you can learn for that kind of case. With the probabilities, I'm not sure we had a lot of problems with that, actually. I mean, so because it's really a probabilistic model, right? I mean, Problog is based on graphical models. So the probabilities that you get, also if there's a neural network in there, is in line with the probabilistic graphical model semantics and meaning. So yeah, we didn't experience problems there so far. Maybe I don't fully get the question as well.
Yeah, I guess what I meant more was like, have you tried this in a setting where the neural attributes, the correct probabilities should have been like 50-50? Because my intuition is that getting the calibration correct, that it outputs actual probabilities, may be more difficult if the probabilities aren't like 100% on like a correct answer. And rather you really need to do like inference over uncertainty.
Yeah. Well, I guess like this little example with this one is like, yeah, you get noisy is like a probability, right? It's 20%, 40%, something. Also with the cards, where you really predict probabilities, like what's the probability that you win in poker with a particular hand in a particular situation. These are real probabilities that you try to predict, and in some cases it worked here, not in all the cases, but that was mainly because of the scalability problem. I think if we would do that now, it would work much better. So
Okay.
so really trying to
I guess I won't push this point too much further, but I guess like in this case, the output of the neural network is still to recognize the cards. It's not going to output like 50% chance of the jack being a jack or a queen.
No, but it's like, I mean,
right?
the
Like
poker,
the predicates are the correct input, the correct output of the predicate is like 100% on one class.
no, it's
And
not,
and
because
the reasoning is unclear on what the last card is, but is that something the neural network is also outputting? It's a distribution on what the last card should be, or is that an output of the system with the logic you've provided?
No, it's basically what it tried to predict here is the probability that with this hand you would win. And that's a probability that was being produced here. So it was producing a probability. As you see, it worked in like 6 out of the 10 experiments, but that was a scalability problem.
Okay.
So I think it can do this, actually. That should not be a problem, because it's inheriting the semantics of this probabilistic modeling language. So yeah, I wouldn't expect problems there.
Yeah, I think I guess it seems like the loss function should help calibrate the probabilities, whereas I think the comparison to an end-to-end neural network, those tend to have overconfident probabilities, but this might help mitigate that. Yeah. I think we maybe have time for one more quick question. We're almost at
I was wondering if it's possible to get to access the recording of this presentation.
Oh yeah, we'll make that available after that.
Thanks.
Okay. Yeah, I guess if there are no more questions, then yeah, thanks so much for joining again for the great talk, and I'll see everyone else at the next webinar next month. Thank you.
Thanks.